Hi everyone. In this video, we will discuss about the analysis of flanger sections. In the case of flanger sections, there are two different types of analysis. First one, depth of neutral axis is less than or equal to depth of the flange. It means that neutral axis is within the depth of the flange. That is case number 1. Case number 2, this depth of neutral axis will be outside the depth of the flange. This is case number 2, right? Case number 1, depth of neutral axis is less than depth of the flange and depth of neutral axis greater than depth of the flange. It means that neutral axis is within the flange, neutral axis is outside the flange. These are the two cases. See, when the depth of neutral axis is within the flange, the analysis is remains same as rectangular portion. As we discussed in the case of rectangular portion, same C value will be 0.36 into B into XU and T value will be 0.87 FIAST. To get the neutral axis, we need to equate C is equal to T, and the distance between C and T, which is known as lever arm, is D minus 0.42 XU. Right? The moment of resistance can be calculated by compression force into lever arm or tensile force into lever arm. That is 0.36 FCK B into XU into lever arm D minus 0.42 XU, or in the case of steel 0.87 FIAST multiplied by D minus 0.42 XU. Right? The complete analysis is remains same as analysis of rectangular portion. As I said, the second case is that depth of neutral axis is greater than depth of the flange. Depth of neutral axis is greater than depth of the flange. Here we have another two cases. In case number 1, depth of the flange by effective depth ratio. The ratio of depth of the flange by effective depth is less than 0.2 and the ratio of depth of the flange by effective depth ratio is greater than 0.2. It means that generally, see, for example, this is the flanged section or T-beam, in which the rectangular portion, the outermost fiber will be 0.45 FCK, right? This 0.45 FCK stress remains up to the end of the flange. The complete depth of the flange is reached the stress of 0.45 FCK. Means the complete rectangular portion will be occupied up to the depth of the flange. This is case number 1. If the dF by D value is less than or equal to 0.2, complete depth of the flange is stressed up to 0.45 SK. Means the rectangular portion will be up to the depth of the flange. If the ratio of depth of the flange by effective depth ratio is greater than 0.2, it means that the compressive stress force 0.45 FCK, the compressive force is not uniform across the depth of the flange. It means that only certain portion is reached the 0.45 FCK. In earlier case, complete depth of the flange is stressed at the level of 0.45 FCK. But here, only certain portion of the flange is reached the 0.45 FCK. Right? Means only a certain depth of the flange is having the rectangular portion. In earlier case, complete depth of the flange is having the rectangular portion. This is the main difference. Okay, this is the main difference. Next, as I said, in case number 1, the formulas remain same, the equations remain same as in the case of rectangular section analysis. But in the case of 2, where the neutral axis is below the flange, we have two cases. The ratio of depth of the flange by effective depth ratio less than 0.2, and the ratio of the ratio of depth of the flange by effective depth ratio is greater than 0.2. Now we will discuss about the equations involved in the analysis of df by d ratio less than or equal to 0.2. Okay, what I said, when the df by small d value less than or equal to 0.2, the complete depth of the flange is stressed to the 0.45 fck. Am I right? Complete depth is having uniform compressive force of 0.45 fck. In this case, I am dividing these stress blocks into two categories. In first category, I am considering only the rib portion. Only rib portion. See, this is only the rib I have considered. And the again I considered only the flange portion. I removed this rib. Okay. To analyze this section, I have taken stress block of rib and stress block of flange separately. Coming to the rib portion, see, now this is the rib. The complete flange is in the stress of 0.45 fck, and certain portion below that flange is also having the stress of 0.45 fck. This is the complete portion, right? It is similar as in the case of rectangular portion, right? So here these formulas also same as in the case of rectangular portion. Same, the outermost fiber is reached the stress 0.45 fck. The compressive force will be at distance of 0.42 xu. The distance between compressive force and tensile force will be d minus 0.42 xu. Okay, d minus 0.42 xu. Okay, no issue with this part. Now I am considering only the flange section. Only flanged portion I am taking here. Flanged portion. See, the complete width of this flange will be BF. Now I am removing this web portion. That's why BF minus BW. Right? Here I have half portion. Here I have another half portion. That's why BF minus BW by 2. This is the BF minus BW by 2. This is BF minus BW by 2. Right? Now here the complete depth is reached the 0.45 fck stress. Okay, 0.45 fck. Complete depth reached 0.45 fck. That's why CF will be 0.45 fck multiplied by area of this portion, right? Area of this portion 0.45 fck into 0.45 fck into 0.45 fck into bf minus bw multiplied by depth of the flange depth of the flange. This is the equation for total compressive force of the flange 0.45 fck into bf minus bw into depth of the flange, right? Where it will act at the distance of df by 2. Am I right? Why? Because it is a rectangular portion. That's why it will act at a distance of df by 2, right? Here, hope you are clear. In the case of the section where the neutral axis is below the flange, we have separated the analysis of rib portion and flanged portion separately. In the case of rib portion, the equations remain same as in the case of rectangular portion, but in the case of rib portion, the compressive force will be 0.45 fck multiplied by breadth of the flange minus breadth of the web multiplied by depth of the flange. This force will act at distance of half of the depth of the flange. Okay, the formula for tension remains same, right? Next, coming to this compressive force. Now here compressive force means the sum of web compression and flange portion compression. The web portion will be 0.3 fck b into sq plus flange portion will be 0.45 fck multiplied by bf minus bw into depth of the flange. Tension is remains same 0.87 FIAST. Now total moment of resistance equals to moment of resistance offered by web portion and moment of resistance offered by flange portion. As I said, compressive force of the web multiplied by lever arm is remains same d minus 0.42 SU. But in the case of flanger portion, the lever arm will be, this is complete effective depth, right? This is d. D minus df by 2 will give the lever arm in the case of flanger portion, right? Here this is the lever arm, right? Now df by d value greater than 0.2. Sorry, df by d value greater than 0.2. Okay, in this case only certain depth of the flange stressed up to 0.45 sek. Okay, only certain depth of the flange is having uniform cross section of 0.45 fck. In this case also, I am going to analyze rib portion and flange portion separately. See, coming to the rib portion, only certain depth is reached 0.45 fck stress level. This portion only, right? In this case, the equations for CW means compressive force in the web is 0.36 fck b into xu. Okay, as in earlier case, right? TW will be 0.87 FIAST. We can say it is a AST. Here T is remains same. Okay, T is remains same in web portion and flanged portion. Okay, same value. Next, Coming to the flanged portion, right? Here only certain portion of depth of the flange is reached the stress of 0.45 ck, where here uh, there is a small change. Instead of depth of the flange, we are taking YF. This is a modified thickness of the flange. Here we are modifying this thickness of the flange. Why? Because in earlier case, complete depth of the flange is reached the stress. But here only certain portion reached the uh, stress of 0.45 ck. That's why I am assuming uh, this total flange the total flange up to the depth of YF has been reached this stress level. Now I am modifying this depth of the flange. Depth of the flange is modifying as YF. YF. This is the modified thickness of flange, which is equal to YF. YF is equal to 0.15 times XU plus 0.65 times DF, depth of the flange. 0.15 times of XU plus 0.65 times of depth of the flange. Right? Now we can use the same formula as in the case of df by d less than or equals to 0.2, but here simply we need to replace depth of the flange with YF, where YF is 0.15 XU plus 0.65 DF. See, in earlier case it is small d minus effective depth minus depth of the flange by 2. Here we are replacing the depth of the flange capital DF with small yf by 2, modified thickness of the flange. Remains same. Remaining equations are same. Compressive force of the flange will be 0.45 FCK, 0.45 FCK multiplied by breadth of the flange minus breadth of the web multiplied by, here we need to write DF, but here we are writing YF. YF means this one, right? Now coming to the moment of resistance, this force into lever arm 0.36 FCK, 0.36 FCK, B into XU into lever arm will be D minus 0.42 XU plus this force, compressive force in the flange, that is 0.45 FCK, breadth of the flange minus breadth of the web into modified thickness YF multiplied by, what is the lever arm here? D minus YF by 2. This is the moment of resistance in the case of the ratio of df by small d greater than 0.2, right? We will solve one or two problems in each case in coming videos. Thank you.